This lecture we're going to talk about power series. If you're following Stuart's book, we will be skipping sections 11.8 and 11.9, but we'll introduce the material we need from there as we go along. So firstly, I want to recall a few things. First thing, a series, sum n equals 1 to infinity a n, is defined to be limit k goes to infinity of sk, where sk is the kth partial sum. That's you add up the first k things. So this is the limit k goes to infinity of add up the first k things. You add up one thing, then you add up the first two things, then you add up the first three things, and you add up more and more and more and more. And this limit is this, I put it in quotes, idea of adding up all of the terms, adding up infinitely many terms. Okay, second thing, a geometric series, this is a special type of series, is a series of the form sum n equals 0 to infinity a r to the n. And that is a plus ar plus ar squared and so on. A is called the first term for obvious reasons. And R is called the multiplier or common ratio. Okay, so the special thing about a geometric series is you start off with a number a, and to get to the next term you just multiply by r, and you keep multiplying by r and putting plus signs down. Okay, that's a geometric series. Now we showed before, for r, absolute value of r less than 1, this series converges. And in particular, it converges to a over 1 minus r. We also showed for absolute value of r greater than or equal to 0, this series, a r to the n, does not exist, i.e. the limit does not exist. If you keep adding up more and more terms, this limit does not exist. You can say the series does not converge, etc. Okay, so let's start a new page. Okay, so I want to make a quick remark before I move on to the next point. For each r, let's just think of a as being 1, this geometric series is a different series. You can think about r as being a half, r as being a third, r as being 7. Each different r gives you a different series. Now we know that for each r with absolute value of r less than 1, this series is a number. So for each of these r's, this series is a different number. Now, why am I mentioning this? So, we could think about inputting r, again with absolute value of r less than 1, and outputting this number, this series, sum r to the n. And in particular, this equals 1 over 1 minus r when we have this condition on the size of r. So what does this remind us of? Inputting a number and outputting another number. This brings me to my third point. A function is, in a hand-wavy kind of way, a machine. We think about plugging in an x into the machine, let's call it f. We usually call the input x, the machine f, and the output is f of x. So what is this to do with geometric series? Well, we can think about plugging r into the geometric series machine, g, and getting out r to the n, this geometric series. Now, this machine only makes sense if the inputs have absolute value less than 1, because otherwise the output is going to be nonsense. It's going to be some sort of series that doesn't even converge. So we have taken an idea of a series and developed an idea of a function from it. And this is going to be the entire point of the discussion in this lecture. We are going to establish some sort of connection between functions and these special types of series. And that's going to be the goal of the lecture. Okay, so let's start with the first definition of the lecture. Definition. A power series centered at 0, and this will become relevant later, is a series of the form sum n goes from 0 to infinity Cn x to the n, where x is a variable and the Cn's are constants called the coefficients of the series. Okay, so going back to this idea of a function, we think about taking x, inputting it into this power series machine, and what we get out is this series, Cn x to the n, goes from 0 to infinity. If we were to write this out in the dot 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 notation, that would be C0 plus C1 times x, plus C2 times x squared, plus C3 times x cubed, and so on and so on and so on. Okay, let's look at some examples. Firstly, sum x to the n equals 0 to infinity. So here the Cn is just 1, because if we were to write this out, it would be 1 plus x squared plus x cubed, so the Cn's are all just 1. Second example, x to the n over 2 to the n. It goes from 0 to infinity. And we can see again here that Cn is 1 over 2 to the n. Okay, so remark, the Cn's are really what determines the power series. So different Cn gives you different series. You always have this x to the n, but it's the Cn that controls which series it is. So different Cn's give different series. Now, fundamental question. If we want to think of this as a function, if we want to think of it as a machine, what is the fundamental question for any machine? Well, that is, what can you put into it? For what values of x does the series sum n goes from 0 to infinity Cn x to the n make sense? What x's can you plug into this machine? i.e., for what values of x does this series converge? And that's going to be the fundamental question when talking about power series. If I'm to define one of these power series, if I'm to tell you what the Cn's are, you need to ask, well, what values of x does it make sense to plug into this machine? Okay? Now, we'll develop more sophisticated tools for answering this question in the next lecture, but we're going to see some examples of figuring out what values of x make sense to plug into different types of power series in this lecture as well.